From the dawn of humanity, we've gazed up at the cosmos. Stars twinkled above our ancestors' campfires just as they do above us today. Space exploration is the ultimate expression of our curiosity. It's about pushing the boundaries of human ingenuity, daring to venture beyond Earth. Building a spacecraft isn't like assembling a car or constructing a skyscraper. Every component, every weld, every line of code is critical to a successful mission. Imagine holding a piece of the spacecraft in your hand, a fragment of metal destined for the stars. The process begins with the selection of materials. We're talking about alloys capable of withstanding extreme temperatures, composites that are both lightweight and incredibly strong. Think of the heat shield, a spacecraft's armor against the searing heat of atmospheric re-entry. The assembly process itself is a marvel of modern engineering. Every bolt, every wire, every piece of insulation is meticulously inspected and tested before being integrated into the larger structure. While the journey to space captures our imagination, it's the return that truly highlights the ingenuity of space travel. Re-entry is a controlled fall, a delicate dance with the forces of gravity and atmospheric drag. As the spacecraft plunges back into Earth's atmosphere, it encounters friction generating intense heat. The spacecraft's angle of re-entry is crucial. Too steep, and it burns up like a meteor. Too shallow, and it could skip off the atmosphere. As the spacecraft descends further, it deploys parachutes, ensuring a safe splashdown. Imagine a giant jigsaw puzzle, but instead of cardboard, it's made of gleaming metal alloys, advanced composites, and intricate circuitry. Unlike buildings on Earth, spacecraft are subjected to the unforgiving environment of space. Extreme temperatures demand materials that can withstand wild fluctuations without losing their structural integrity. Spacecraft need specialized shielding to protect both sensitive electronics and the human crew. Micrometeoroids and space debris pose another threat. Spacecraft exteriors incorporate layers of lightweight but strong materials to disperse the energy of an impact. Every weld, every joint, every connection point is critical. Section 2. The heart of the matter: propulsion systems. In a spacecraft, the propulsion system provides the thrust needed to break free from Earth's gravitational embrace. The most common type of spacecraft propulsion relies on chemical rockets. Liquid-fueled rockets offer high thrust and are ideal for launching heavy payloads into orbit. Solid-fueled rockets are simpler in design and offer high thrust over short durations. Beyond chemical rockets, scientists are exploring more efficient forms of propulsion like ion propulsion and solar sails. The choice of propulsion system depends on the specific mission requirements. Section 3. A breath of fresh air: life support systems. A life support system provides the essential elements for human survival within the confines of a spacecraft. It needs to constantly replenish oxygen while removing carbon dioxide. Some advanced systems are experimenting with growing plants on board. Temperature regulation is critical, using a combination of insulation, heaters, and cooling systems. Water recycling systems purify wastewater, making space travel a closed-loop endeavor. The life support system ensures that the cabin pressure remains at a safe and comfortable level. Section 4. Assembling the puzzle: the art of spacecraft construction. Building a spacecraft is a highly specialized, meticulous process that takes place in pristine clean rooms. The process begins with the fabrication of individual components using computer-aided design. Once the components arrive at the assembly facility, they undergo rigorous inspection and testing. Large components are carefully maneuvered into place using overhead cranes and robotic arms. Smaller components are painstakingly installed by hand. The spacecraft undergoes a battery of tests to simulate the harsh conditions of space. Section 5. Eyes and ears in the void: sensors and communication. Navigation sensors provide the spacecraft with a sense of direction and position. Star trackers determine the spacecraft's orientation by locking onto the positions of known stars. Inertial measurement units track the spacecraft's movements with incredible accuracy. Spacecraft rely on scientific instruments to collect data about their surroundings. Communication systems transmit and receive data via radio waves. The data collected forms the backbone of our understanding of the cosmos. Section 1. Trial by Fire, Extreme Temperature Testing. Space is a realm of extreme temperatures, a stark contrast to the relatively balmy conditions we enjoy on Earth. Thermal testing is a crucial stage in spacecraft development. Engineers subject the craft to simulated space environments to ensure its materials, components, and systems can handle the thermal extremes of spaceflight. One of the primary tools used in thermal testing is a thermal vacuum chamber. Engineers carefully monitor the spacecraft's performance throughout these thermal cycles. The goal is to ensure the spacecraft can operate flawlessly in the face of temperature extremes. Section 2. Shaken Not Stirred. Vibration and acoustic testing. Launching a spacecraft is a violent affair. Imagine strapping yourself to a giant firecracker and blasting off into the sky. These forces can shake a spacecraft apart, causing catastrophic damage. Vibration and acoustic testing subjects the spacecraft to controlled forces. It's like a rigorous shake test at a rock concert. Engineers use hydraulic actuators to simulate launch vibrations. Acoustic testing focuses on intense sound waves from rocket engines. The spacecraft is wheeled into a massive acoustic chamber. Powerful speakers blast the spacecraft with deafening noise. Engineers monitor the spacecraft's response using accelerometers. They're looking for signs of excessive vibration or acoustic damage. The data helps identify design modifications or reinforcements. It's a testament to the meticulous attention to detail in spacecraft engineering. Section 3. Vacuum Symphony, Simulating the Void. Space is a vacuum, a concept that's hard to grasp here on Earth. This absence of air has profound implications for spacecraft design and testing. Engineers use vacuum chambers to simulate space conditions. These chambers can evacuate almost all air, creating a near-space environment. Inside, they test spacecraft systems, ensuring they function flawlessly. From fuel tanks to solar arrays, every component is scrutinized. Thermal testing is also crucial as heat transfer differs in space. By simulating space conditions, engineers ensure spacecraft readiness. Section 4. Radiation Gauntlet, Shielding Against the Invisible. Beyond Earth's atmosphere, space is awash in radiation, a constant barrage of high-energy particles. This radiation poses a significant threat to spacecraft electronics and astronaut health. Protecting spacecraft involves a multi-layered approach combining material science and shielding design. Passive shielding uses dense materials to absorb and deflect radiation. Active shielding uses electric and magnetic fields to deflect charged particles. Mission planners minimize radiation exposure by choosing safe trajectories and timing activities. As we venture farther into space, effective radiation protection becomes crucial. Section 5. The Human Factor, Astronaut Training and Simulations. Astronauts undergo rigorous training to prepare for space. This includes physical conditioning, mental preparation, and technical skill development. Physical training builds endurance and strength, essential for microgravity. Mental preparation ensures astronauts can handle isolation and stress. Technical training covers spacecraft systems and emergency procedures. Simulations and VR provide realistic practice for space missions. This comprehensive training ensures astronauts are ready for the challenges of spaceflight. Years of planning, billions invested, countless hours of engineering, all culminate in this, the launch sequence. A symphony of controlled explosions and roaring engines propels astronauts from Earth into space. Final checks, meticulous inspections, and immense pressure. Engineers swarm the rocket, their movements precise. Astronauts undergo pre-flight checks, calm and steady. The countdown clock ticks down, tension palpable. Launch Control Center falls silent, eyes on monitors. The air crackles with anticipation. At T-minus 10 seconds, engines ignite, shockwaves ripple. The ground shakes, air vibrates, smoke engulfs launch pad. The sound is deafening, primal. The rocket rises, a plume of fire tracing its ascent. Astronauts feel the force, leaving Earth behind. The journey into space is not a single dramatic event but rather a carefully orchestrated series of phases, each with its own unique challenges and objectives. From the moment the rocket clears the launch tower to the delicate maneuvers required to achieve orbital insertion, every step is critical to the mission's success. The first few minutes after liftoff are the most violent and dynamic. As the rocket climbs through the thickest part of Earth's atmosphere, it experiences intense aerodynamic drag, buffeting the spacecraft and its occupants. The roar of the engines, combined with the shaking and rattling, creates a sensory overload that tests the limits of human endurance. As the rocket ascends, it sheds its massive first-stage boosters, their fuel spent, their fiery descent back to Earth, a spectacular but carefully controlled pyrotechnic display. The second-stage engine ignites, continuing the push towards space, the acceleration building as the rocket sheds more weight. The sky transitioning from deep blue to the inky blackness of space. Once above the atmosphere, the rocket typically jettisons its payload fairing, the protective shell that shielded the spacecraft during its fiery ascent. With the fairing gone, the astronauts get their first unobstructed view of Earth, a breathtaking blue and white sphere suspended against the backdrop of the cosmos. Now in the microgravity environment of low Earth orbit, the spacecraft performs a series of delicate maneuvers to adjust its altitude, inclination, and speed, eventually rendezvousing with the International Space Station or deploying a satellite into its designated orbit. These maneuvers, often controlled by onboard computers with assistance from ground control, are a testament to the precision and sophistication of modern spacecraft navigation. Living and working in space is a far cry from life on Earth. Imagine spending months confined within the cramped quarters of a spacecraft. It's a testament to the adaptability of the human spirit. The absence of gravity presents unique challenges to everyday life. Simple tasks like eating and sleeping become complex procedures. Food often comes in dehydrated or pre-packaged forms. Astronauts strap themselves into sleeping bags to prevent drifting. There's no up or down in space, just weightlessness. Hygiene also requires adaptation. Showers are replaced by sponge baths. Toilets use air suction instead of water. Exercise is essential for counteracting bone and muscle loss. Astronauts spend hours each day exercising. They use specialized equipment to simulate resistance training. Section 4 Spacewalks Ballet in the Void. Few experiences rival the awe of a spacewalk, a lone figure in a white suit tethered to a spacecraft. It's a ballet of delicate movements in a hostile environment. Spacewalks, or EVAs, require specialized suits providing life support and protection from space hazards. Astronauts meticulously check their suits, ensuring every system functions flawlessly. They pre-breathe pure oxygen to avoid decompression sickness. Outside, they rely on tethers and handrails, moving slowly with limited dexterity. The silence, broken by breathing and radio, is surreal. Spacewalks serve various purposes, from experiments to repairs. Astronauts install modules, deploy satellites, and repair telescopes. Section 5 The Science of Discovery, conducting experiments in microgravity. Beyond the spectacle of spaceflight, microgravity offers unique scientific opportunities. Flames burn in perfect spheres, liquids form perfect droplets, and crystals grow symmetrically. This opens new realms of scientific inquiry. Materials science and fluid dynamics benefit greatly. Biology also gains insights into life mechanisms and space travel effects, paving the way for future missions to Mars and beyond. Section 1. The Fiery Return. Navigating Atmospheric Re-entry. Re-entry is a delicate dance between gravity and aerodynamics, transforming kinetic energy into heat. The spacecraft encounters increasing air density, creating friction and intense heat. Too steep and it burns up, too shallow and it skips off the atmosphere. Extreme deceleration forces push astronauts back into their seats. The windows glow red-hot, a testament to the extreme conditions. This perilous journey back to Earth is a routine aspect of space travel. Section 2. A Balancing Act. The physics of re-entry angles. The angle at which a spacecraft enters the Earth's atmosphere, known as the re-entry angle, is not a matter of guesswork or luck. It's a critical parameter meticulously calculated and fine-tuned to ensure a safe and successful return. It's a balancing act, a delicate dance between utilizing atmospheric drag for deceleration while minimizing the intense heat generated by friction. Imagine a flat stone skimming across a pond. If you throw it at a shallow angle, it bounces off the surface, its horizontal momentum barely slowed. Throw it at too steep an angle and it plunges straight down, its journey cut short. The same principle applies to spacecraft re-entry, but with much higher stakes. A shallow re-entry angle, typically less than 7 degrees below the horizontal, allows the spacecraft to gradually bleed off speed as it encounters the increasing density of the atmosphere. This approach minimizes peak heating but extends the duration of the re-entry phase, requiring the spacecraft to withstand prolonged exposure to high temperatures. A steeper re-entry angle, typically between 7 and 20 degrees below the horizontal, results in a more rapid descent and higher peak heating, but shortens the overall re-entry time. This approach is often used for missions returning from higher orbits or lunar missions, where minimizing the time spent exposed to the harsh re-entry environment is crucial. The optimal re-entry angle depends on various factors, including the spacecraft's velocity, mass, shape, and the specific mission requirements. For crewed missions, minimizing the G-forces experienced by the astronauts is a paramount concern, influencing the choice of re-entry trajectory. Section 3. Shielding from the Inferno, the role of heat shields. As a spacecraft plunges through the Earth's atmosphere, the friction generated by its immense speed and the increasing air density creates an inferno of heat, with temperatures soaring to thousands of degrees Fahrenheit, hot enough to melt even the most robust metals. Protecting the spacecraft and its precious human cargo from this intense heat is the job of the heat shield, a marvel of materials science and engineering. Unlike the rest of the spacecraft, typically constructed from lightweight alloys and composites, the heat shield is designed to ablate, meaning it gradually vaporizes and carries away heat during re-entry. Think of it as a sacrificial layer, absorbing the brunt of the thermal energy and protecting the underlying structure. Early heat shields, used in the Mercury, Gemini, and Apollo programs, were made of ablative materials like fiberglass and phenolic resin. These materials, when exposed to high temperatures, undergo a process called pyrolysis, breaking down into gases that carry away heat and leave behind a charred protective layer. Modern heat shields often utilize more advanced ablative materials, such as carbon phenolic and PICA, which stands for Phenolic Impregnated Carbon Ablator. These materials offer a higher heat capacity, meaning they can absorb more heat before reaching their ablation temperature, and they produce a more stable and predictable char layer during re-entry. The shape and thickness of the heat shield are also crucial to its effectiveness. The blunt body design, a rounded shape that creates a shock wave ahead of the spacecraft, helps to dissipate heat and reduce the heat flux, the rate of heat transfer, to the spacecraft's surface. Section 4, from supersonic to subsonic, deceleration and parachute deployment. As a spacecraft descends further into the Earth's atmosphere, the increasing air density provides natural braking, slowing its descent from supersonic speeds, faster than the speed of sound, to subsonic speeds, slower than the speed of sound. This transition, marked by a dramatic decrease in heat and vibration, signals the final stage of the re-entry phase. Imagine a supersonic jet breaking the sound barrier, creating a deafening sonic boom. During re-entry, a spacecraft goes through a similar transition, but in reverse, slowing down from hypersonic speeds many times the speed of sound to subsonic speeds. This deceleration, while less dramatic than the fiery initial phase of re-entry, is no less critical to a safe landing. Once the spacecraft has slowed to a manageable speed, typically a few hundred miles per hour, it deploys a series of parachutes, large fabric canopies that increase air resistance and further slow the descent to a safe landing speed. The timing and sequence of parachute deployment are critical, ensuring a smooth and controlled deceleration without exceeding the structural limits of the spacecraft or the G-forces tolerable by human occupants. The first parachutes to deploy are typically small drogue parachutes, designed to stabilize the spacecraft and reduce its speed to a level where the main parachutes can be safely deployed. The main parachutes, often brightly colored for visibility, are much larger, resembling giant umbrellas, and they slow the spacecraft to a gentle landing speed, typically around 20 miles per hour. Section 5: Homecoming, Splashdown, and Recovery Operations. After its fiery descent through the atmosphere and the parachute-assisted deceleration, a spacecraft returning from space faces its final challenge: a safe landing, either a splashdown in the ocean or a touchdown on solid ground. While seemingly less dramatic than the preceding stages of re-entry, the landing phase demands its own set of specialized procedures and recovery operations. For crewed missions returning from orbit, splashdown in the ocean has been the preferred landing method since the early days of space exploration. The vastness of the ocean provides a large target, reducing the need for pinpoint accuracy, and the water cushions the impact, minimizing the forces experienced by the astronauts. As the spacecraft descends under its parachute canopy, a team of recovery specialists aboard ships and helicopters closely monitors its trajectory and prepares for retrieval. Divers are on standby to secure the floating spacecraft, ensure its stability, and assist the astronauts in exiting the capsule. Once safely aboard the recovery ship, the astronauts, often weak and disoriented after their long journey, undergo medical checks and begin the process of readapting to Earth's gravity. The spacecraft, its mission complete, is hoisted aboard the ship, ready to be transported back to land for analysis and potential future use. The successful recovery of a spacecraft and its crew marks the culmination of years of planning, engineering, and human endeavor, a testament to our collective ambition to explore the cosmos and push the boundaries of what's possible. Section 1: The Next Giant Leap. From fiery launches to perilous re-entries, space exploration showcases human ingenuity. From Sputnik's grainy images to rovers on Mars, sending high-definition photos, we've built orbiting labs, pushing scientific boundaries, expanding our understanding of the universe. This is just the beginning. Future quests will drive innovation, inspiring generations to come. New propulsion systems promise faster travel, with lightweight materials for deep space. AI-driven spacecraft will operate autonomously, pushing exploration further. Humans on Mars, once science fiction, is now within reach, a testament to human ambition. Beyond Mars lie the outer planets, their moons shrouded in mystery, their rings a celestial ballet. As we venture further, we carry lessons from early pioneers, building on their legacy, their courage and belief in human ingenuity. The journey ahead will be challenging, but the rewards will be immeasurable. In exploring space, we explore ourselves, our potential, and our place in the cosmos.